We'll conclude section 1.2 on the topic of rationalizing radicals. The motivation is that sometimes we have fractions that look like 1 over the square root of 2, and we don't really want these radicals to exist in the denominator. So we can perform actions that look like the following. I'm going to take 1 over square root of 2, and I'm going to multiply it by the square root of 2 divided by the square root of 2. We know that anything divided by itself is equal to 1, so multiplying 1 over root 2 by root 2 over root 2, that term on the right, is essentially the same thing as multiplying by 1. I haven't changed the value of this expression, just the way that it looks. This strategy of multiplication by 1 is essentially the heart of this section, so we're going to talk a lot about that. But for now, let's simplify. Multiplying these fractions gives square root of 2 divided by root 2 times root 2, which simplifies to the square root of 2 divided by 2. I know it's a lot of 2's in one place, but what we've got is a fraction that is the same as what we started. It is just written differently. Instead, I have the square root of 2 in the numerator and a 2 in the denominator. And that's the whole point of rationalizing the denominator, is multiplying by a term such that when I'm done simplifying, I have no more radicals in my denominator. As we said, multiplication by 1 is going to be the heart of this section. We use that term root 2 over root 2, which numerically is equal to 1. Pretty much if any algebraic expression a is divided by itself, it becomes the number 1. So we can use terms like big A divided by big A because it's numerically equal to 1 and serves as a very nice manipulation tool. It allows us to change the shape or the form of our algebraic expression without actually changing its value. The only thing we have to be careful of is ensuring that a is not equal to 0. This is because 0 divided by 0 is undefined and is certainly not equal to 1. The first type of problem that we're going to have, what we'll call case 1, is where I only have one radical term in the denominator. What we did last time was we forced the term the square root of 2 squared to show up because then the radical and that power cancel each other out. And that's the sort of thing that we want to force here. So suppose I've got the term 1 divided by the cube root of 4xy squared. I have a radical in the denominator, but now the situation is a little bit more complicated. But I do know if that every single term inside the radicand had a power of 3, those powers of 3 and the index of 3 would all cancel each other out. So that's the kind of thing we want to work on here. The first thing I'll do is take every single thing inside the radical and write it as a power of something. I can rewrite the inside as 2 squared x to the first y squared. Now everything has some kind of exponent. But here I want everything inside the radical to have a power of 3. So what if I increase the power of 2 by 1, increase the power of x by 2, and increase the power of y by 1? If I do that, each thing will have a power of 3. So that's how I'm going to construct my multiplication by 1 here. I'm going to start the construction of our multiplication by 1. The denominator is going to be the cube root of 2 to the first, x squared, and y to the first. So this additional radical is giving me the exact exponent additives that I need so that when this simplifies, everything in that radical downstairs has a power of 3. But because I built this term in the denominator, I need to copy it in the numerator. Otherwise, I wouldn't be multiplying by 1. And once I multiply these fractions out, I obtain the following result. And as desired, everything downstairs, just by the properties of exponential addition, everything in the radical downstairs has a power of 3. This also means that that index and all those exponents cancel each other out. So I get a final answer of the cube root of 2 to the first, x squared, y to the first, divided by 2xy. It's okay that radical terms are stacking up in the numerator. That's okay because the point is to rationalize the denominator, so terms are going to stack upstairs. For our next example, we'll look at another case. The fifth root of minus 4 times x to the 6th divided by 8y squared. The first thing we'll do is take the fifth root of the numerator and denominator separately, and then we are going to write everything in the denominator radicand as a power of something. I can write 8 as 2 to the third, and y squared as, well, as y squared. Now everything in that denominator radicand needs a power of 5. So I can increase the exponent of 2 to the third by 2, and I can increase the exponent of y squared by 3. Doing so, I will introduce the new term, the fifth root of 2 squared times y cubed. Since I built this term in the denominator, I need to copy it in the numerator so that my multiplication of 1 is complete. Next, I'll multiply these fractions. I will combine all the exponents within both radicals, and then I'll simplify. And then I'll see that every term in the denominator radicand will have a power of 5. And then the numerator terms are just going to stack up however they stack up. Some might cancel out, some remain in the radical. It just depends on the problem. But the cancellations that take place now are similar to those from the last video. I'm going to end up with negative 2x times the fifth root of xy cubed divided by 2y. And once I let those 2's cancel, I get negative x times the fifth root of xy cubed divided by y, and we're done. And that's it for the case 1 examples that we'll show here, the cases where I only have one denominator. Take a look at the notes if you need to, but remember I'm trying to multiply 1 in a very special way such that every exponent in the radicand for the denominator matches the index. In the next case, we're going to look at what happens when I've got two terms in the denominator. This might look like a sum or a difference, for instance, square root of 2 minus square root of 3. Let's do a little background information first. We need to understand something known as the difference of squares formula. Observe that if a and b are two algebraic expressions, then the quantity a plus b times a minus b, when we FOIL this out, comes down to a squared minus b squared. And these middle terms simply just canceled out, and the only surviving terms that I have are the squares. That's why this is known as a difference of squares, and we'll also see later on that this is a nice factoring formula. But the key observation here is that a plus b and a minus b both have different signs in the middle. This is known as the concept of conjugates. The conjugate of the quantity a plus b is a minus b. And likewise, the conjugate of the quantity a minus b is a plus b. Essentially, I take a sum and I turn it into a difference, or vice versa, and I get the word conjugate. So, what if I multiplied the square root of 2 minus the square root of 3 by its conjugate? Once I multiply these things out, I'll notice that by FOILing, those middle terms cancel, and I just get left with 2 minus 3, which is equal to minus 1. Because the first and the last terms were square root of 2 squared and square root of 3 squared. Those squares and square roots canceled out, so I just got the 2 and the 3 as a result, which subtracted to give me negative 1. So the idea is that if I have a sum or difference of radicals and I multiply them by their conjugates, the final result will be not a radical value, but an integer value. And that's really what we're going to focus on here. Just to keep the algebra familiar, we're essentially going to upgrade what we just did. I'm now going to consider the term 1 divided by square root of 2 minus square root of 3. We're again going to perform this idea of multiplication by 1. What I'm doing here is something known as multiplying by the conjugate. I've taken the original quantity and multiplied it by the conjugate of root 2 minus root 3 divided by itself. And because of the algebra that we did on the last slide, we know that root 2 minus the root 3 multiplied by root 2 plus the root 3 will simply just turn into the number negative 1. So let's see this in action. We'll multiply these fractions together. We'll go ahead and FOIL out or use our difference of squares formula on the denominator terms. We'll go ahead and simplify. And we see that we get a final answer of root 2 plus the root 3 divided by negative 1. Now, since the denominator is simply just a negative 1, I can do a little bit more algebra to at least get rid of the fraction altogether, but the final result is still what we wanted. I have cleared all radicals from the denominator. So at the end of the day, the overarching strategy for the case where I have a sum or difference of terms in the denominator means I'm going to multiply by the conjugate. This process ends up being a little bit more straightforward than case 1 because I don't have to think too hard about how the term is constructed. I multiply by the conjugate by changing a plus to a negative or vice versa, and then I have my multiplication by 1. The nice thing is that this process also works well with variables. Suppose that my quantity looks like 2 times root x plus root y divided by root x minus root y. I multiply by the conjugate. And the conjugate in this case is going to be the square root of x plus the square root of y divided by square root of x plus the square root of y. The original denominator term had a negative sign, so I change it to a plus. I have to FOIL my numerator, but my denominator simplifies just by the difference of squares formula. So when I FOIL my numerator, it looks like 2 times root x squared plus 2 root x root y plus root x root y plus the square root of y squared. And my denominator is the square root of x squared minus the square root of y squared. Clearly that's fun to say 5 times fast. But let me just look at what I've got. I'll combine like terms, I'll simplify expressions, and I'll find a final answer of 2x plus 3 root xy plus y divided by x minus y. Therefore, my denominator has no radicals as desired. As an exercise, start with this original problem and take that denominator and change it into a root x plus root y, and then multiply by its conjugate. See what happens and see what you get. Otherwise, make sure to ask questions, consult the notes for this video, or watch the video again if you need to. There is a lot of algebra here, so making sure you're also trying to take some notes while doing this is going to be a good idea. This does conclude the topics for section 1.2, so join us for section 1.3.